Hello, everybody. Okay. So I'm going to be here for like an hour and a half talking about various things. The first part is to talk about like old and new primitives. This is a presentation. It's going to take like 20 minutes. And then after that, we're going to have a panel with me, Ellie, Vitalik, Yajang, and Jordi. And we're all going to talk about like ZKPs. We're going to have like a long discussion about all things ZKP. So yeah, let's get started. So this talk is to talk about like old primitives and new primitives. So we want to do like a lot of things with zero knowledge proofs, and like sometimes it can be difficult to build all of the things that you need to make a product. So one of the things that PSE has been doing is that we've been trying to build like primitives. We try and make tools for people to use so that we're able to reduce the amount of work that someone needs to do in order to build a ZK application. So like the first ZK application in the wild was like Zcash, and this was something that lets you like transfer money to other people privately. And basically the way that Zcash worked is you needed to have like a proof of membership that you could do inside a zero knowledge proof. So you can prove that like you're part of a group without revealing who you are. And that's basically what we've implemented with Semaphore, is like a generic proof of membership. And we're working on a whole bunch of new tools. And what I want to do is first talk about like Semaphore and like how that has progressed to the point of like being used by people, and then talk about some of the other primitives that are going to be here soon. Cool. So Semaphore can be used for like a whole bunch of different applications. We recently had like a Semaphore grants round where we gave like grant funding to a whole bunch of teams to build applications on top of Semaphore. So we had 35 applications, and there's a whole bunch of different like use cases for it. So some examples of these are like you can use ZK, you can use Semaphore to make like a proof of individuality system. So imagine that like the way that things work at the moment is that like if you want to contribute to Gitcoin or something, you need to pass some like proof of individuality mechanism or screening, because if you weren't, you would be able to just vote like many times, and it kind of breaks the system because you can make as many accounts as you want. So Semaphore allows us to do this, but with privacy. That you would first go through the KYC process, and you would join a Semaphore group, and then afterwards you would make a proof that you're a member of the Semaphore group in order to be able to participate, in order to be able to like donate to Gitcoin or vote in the round or whatever. So it's a nice way of like adding privacy on top. So Semaphore started a long time ago. Like Semaphore was like it was the second ZK application that I made, and I started working on this in 2019. But since then, a whole bunch of other people have been like pushing Semaphore forward, and I've not really been super involved in it. So this is a lot of other people's work since 2019. So the first version of Semaphore is written in C++ in 2019, and it was using this library called Libsnark, which was this like C++ library for making ZK applications. At the time, there weren't really any other like ways to make applications with ZK. So I started, I think I had to port Libsnark to work with Ethereum, and then I started to be able to make some simple proofs, and finally I was able to make Semaphore with it. And then in 2019, we did another version of Semaphore, and this version improved a lot of things, and it also like went a little bit too far, that like we made it so that like Semaphore became this like very secure tool, but it was like too secure because the prover time was very slow. It took a long time to make proofs, and it also had like a lot of these weird dependencies that you needed to worry about. For example, you had to make a signature and then verify the signature inside a ZKP, which was like complicated. And in 2021, we made a better version of this, which was like just very simple. We kind of like merged the 2019 effort and the 2020 effort to get this tool that was super simple and easy to use. And this has been like a really interesting journey for us, because it's like the first time we've been trying to get like a ZK application that people can use, and it's the first time that we like successfully managed to get like people to adopt and start to build on top of this tool. So that's Semaphore, and it's a primitive that people can use, but it's like one of many primitives. There's a whole bunch of other primitives that are interesting and exciting, and that's what I'm going to talk about through the rest of the talk. But like the main thing to take away from the first part is that like this is like one of the things that the PSE is trying to do, privacy and scaling exploration. We're trying to like make primitives so that we can empower other people to make new applications. So here's some like examples of like where Semaphore has been used. So Semaphore is like a proof of membership thing, but it has been used for a whole bunch of different applications. For example, there's a bunch of things about like governance and voting, and there's also like some IoT use cases and some ecosystem use cases. Like maybe you heard about like the Taz experience at DevCon or the Zuzulu passport at Zuzulu, which all use Semaphore to do this proof of membership. So there's just like, it's like our goal is to make like a tool that can be applied to many different use cases. Okay. And here's some more use cases. Proof of individuality, which we talked about before, like some NFT stuff. We have a bunch of social media applications that we can build too, which is like ways of like having like social interactions that are private, and there's a bunch of governance stuff too. Okay, so basically the idea of Semaphore was that like we had cryptography. We wanted to make this system, so we invented our own cryptography, or we used cryptography that other people had invented in order to build like systems that was like very performant. And this was important because zero knowledge proofs, sometimes the proof part is very costly. For example, the first version of Semaphore, it took like a minute to make a proof on my laptop. And this is not good, it takes a long time, it's not a good user experience. If you wanted to have this kind of application for regular users, it would be very frustrating and confusing for them. And it's hard to ask them to wait a long time. So that's why the new version of the version of Semaphore we're using right now is very optimized. But in the same time that we were spending optimizing Semaphore, we were also spending a bunch of time optimizing like ZKPs. So we're getting to the point now where like the proofs that we make don't have to be for special crypto or like new crypto, snark-friendly crypto, but we can use like general crypto that's been around for years. And the key thing to take away, and the reason why this is important is that cryptography is everywhere, all the time. You're going to, like, there's two specific primitives that are really interesting for us to spend some time thinking about. One of them is RSA, which is a signature scheme that was invented like many years ago, and it's used all the time. Websites use RSA when you go to visit the website. Every time your phone connects to a website, you get an RSA signature to say this website is authentic. It's using domain names. Emails is really cool. Every time that Google sends an email to someone, like on your behalf, they attach an RSA signature that says that this is an authentic email that came from Google. We promise, and this is introduced as like an anti-spam mechanism, so that like you could authenticate where emails came from. A whole bunch of government IDs also have RSA signatures. For example, in India, the Aadhaar card has an RSA signature from the government. That's basically the signature of the hash of your name, address, phone number, and a whole bunch of other like personal information. So RSA signatures are everywhere. And one of the limitations with using Semaphore is that we've had to like give Semaphore keys to people. We had to like onboard them and find ways for them to use, find ways for them to give value to the crypto that we're giving out. And this is a lot of friction, right? It's a lot of work to try and convince someone that like, oh, this is important, this is useful, and you have this like chicken and the egg thing where you have to do like more than one thing. Where you want to make a thing that's valuable, but in order for it to be valuable, it has to be useful, and in order for it to be useful, it has to be valuable, and it's just very difficult to kind of close this circle. The other set of primitives that it seems really interesting is ECDSA on P250, the elliptic curve P256. And this is interesting because everybody's phone has like a special chip that when you unlock your phone, it can provide this signature. So this is a really nice like user experience improvement for Ethereum and for other things. So what are we missing with these things? The thing that we're missing with these things is it's just like signature schemes. It's just like once you have a signature, you can show it to someone and they can verify it, but there's no way to have like more complicated rules. And what we're really searching for here is a way to make these primitives programmable. Because one of the really exciting, underrated use cases or reasons why ZKPs are so useful is because they're programmable. That like programmability gives you interoperability, and it also gives you this kind of like permissionless innovation that is really interesting. That it's possible to make like specialized systems for each of the things that we want to do. We could probably make a Semaphore proof that's much more efficient than Semaphore, but then we lose the programmability that we're able to like layer on top. That makes things very, very interesting. Yeah. So who uses RSA? Oh yeah, another example of where RSA keys are used is GitHub. Every time you I don't know if people have set their GitHub profile to automatically sign their commits, but every time you sign your commits on GitHub, like that's an RSA signature. And like you can go to GitHub right now and you can download like millions and millions of RSA signatures from different people. And the cool thing about this is that people are already using this. And these signatures are already valuable because like they're used to authenticate like whether the software that all of the internet is built upon is being contributed to by the people who are claiming to contribute to it. So like one example, really cool use case I would like to see is GitHub wallet. So the vision for this idea is that you have a GitHub repository, or it's a Git wallet. So you have a Git repository that's on GitHub or on GitLab or somewhere else. And basically, in order to make a transfer, what you do is you make a pull request to this repository. When you make the pull request, the continuous integration will do a couple of things. It will check that the pull request is correct. It will take the signature and try to execute this transaction on-chain. If the transaction succeeds, it will merge your pull request into the repository. So we have this really nice use case of like your user interface to Ethereum is just like Git commits and pull requests. And this is a really nice way to start to include the tools that we have in other places. Yeah, so another place that it's really interesting to target these tools is something like smart contract wallets. That like one thing that's really difficult about cryptocurrency is that like when someone loses their private key, this is like the worst user experience ever. Someone like has their private key and they lose it and they lose their money. And like someone loses like $10 or $100, this is the worst user experience you could ever have. I mean, it's really, really terrible. And one thing that we're trying to do to alleviate this is to have many different forms of signatures that people can use to recover their funds if it gets lost. So one example method that we could use is email wallet. The idea here is that you can use the RSA signature that Google assigns to your email address to authenticate your recovery transaction or whatever. And we could go one step further and we could make this kind of like email wallet system where you're able to transfer money using only emails. You can send an email with a subject line, send 10 ETH from me to a certain person or a certain email address or a certain address. And then you can just forward this to some kind of relayer, and then the relayer can process this on-chain and update the blockchain based upon just the signatures that have been assigned by Google or whoever your email provider is. Oops. Okay, so those are two example applications that we were thinking about doing. The ZK email, where you're able to like authenticate like that an email came from a certain person. And here's a couple more example ideas. Like one example idea is like a proof of individuality that you can use because in your emails you have so much information that's unique to you. Like maybe you got an email from the government of your country that included like an ID or something. You could use this as a proof of individuality. You could use a ZKP to verify that the signature on the email is correct, and then you could open selectively some pieces of the email to reveal that you're like a unique citizen of a certain country. Another thing that you could do is you could also use it to export your bank records, your medical records, anything that you've received an email about. And this is really exciting for us because like so far we spent a lot of time making Semaphore and like showing people that okay, you can use Semaphore to make interesting applications, but like there was a lot of headwinds there because we had to try and make it valuable, make it useful for people to have these credentials. And now we're going to a place where we have all of this data, and it's super exciting to think about like all the different things that like we could do with this data. Another example application is you could make this kind of like trustless bridge between like Venmo and crypto. And the way that this basically works is that like every time you send a payment on Venmo, you get an email to say, hey, you've sent this payment. And what I can do is I can make a smart contract on Ethereum that allows someone to deposit money into this contract under the condition that, or allows someone to withdraw money from this contract under the condition that they provide a zero-knowledge proof that has a signature from Venmo on an email that says, congratulations, you've just sent X amount of money to this person. So this can allow us to make these like really fun interactive systems where you're able to like have this kind of like on-off ramp in a decentralized, trustless way. So this is the end of the talk. Is there any questions? Can we take questions? Yeah. Oh, yeah.
All right, we have a question from, hey, thanks. Do you have a sense of how hard it is to break RSA in those cases?
How to prove RSA?
No, sorry, break.
Oh yeah, RSA is targeting 128 bits of security, so it's going to be pretty hard to break the bigger. I think that like the keys that like is used right now is 2024 bits, and I think that's targeting 128 bits of security. So it's going to be as hard to break as like an Ethereum signature. Yeah, it's just another type of signature.